In this part of the lecture, we will continue with looking at the other components of our calculations, and we look at the Dirac equation. But first, let's go about some brief reminder from quantum mechanics. One of the main concepts there is the wave function. So quantum mechanics takes into account the wave-particle duality and implies that one can never predict the exact state of a particle position and momentum with certainty. One can thus no longer represent the state of the particle by a vector position known with unlimited precision at each time t. Instead, the state of the particle is represented by the wave function. So instead of its coordinate, we get a wave function as the function of a coordinate or a function of a momentum. Now, the meaning of the wave function is that the concept of the precise trajectory of a particle is replaced by a probability density to find the particle at a given position at a given time. So probability would be probability density is equal to the square of the wave function, and the probability is computed as probability density times elementary volume. Any measurable physical quantity A can be associated with the linear operator A hat, such as that if one knows wave function psi, the expected value of that quantity can be obtained through such an integral. For position, momentum in one dimension, and energy, the corresponding operators and the expectation values are as follows. So for coordinate, it's just the coordinate itself, and therefore expected value of the coordinate would be represented by such integral. For momentum, the operator of momentum is the derivative by a coordinate, and therefore expected momentum value is found like this. And energy is the derivative in time. Expected value of energy is found from this integral. We know that for two physical quantities to be simultaneously measured, the operators should be commutative, meaning that operators behave in the following way. Examples of commutative operators are components of the coordinate x and y and z, z and x, or different components of momentum, px and py, for example, commute, or also momentum components and coordinate components in different direction. But then if you take x coordinate and momentum also in the same direction, you will see that such a commutator will not be equal to 0. It just means, basically it leads to the Heisenberg uncertainty principle, which you know that uncertainty of measuring the coordinate times uncertainty measuring the momentum should be greater than h/2. And this uncertainty arises due to the matter wave nature of all quantum objects. We can see a graphic representation of the wave-particle duality in this plot, which combines three cases. First case, A, when we have a pure wave with a fixed frequency, which doesn't have any special localization here, but P is well defined. Then second case B is a wave packet with special dispersion delta x and frequency dispersion delta k. And due to the link between the two particle representations, the special dispersion is inversely proportional to the frequency dispersion. And the last case, C, a pure particle, which is localized to some coordinate, but doesn't have a determined frequency. The first quantum mechanical equation was established by Schrödinger for non-relativistic particles. He assumed that the solution should be of the same form as for the electromagnetic wave, therefore looks like this. And he started with the non-relativistic relation between energy and momentum. The energy is equal to p squared over 2m plus potential energy. We multiply it by the wave function and get the following expression. We can take the derivative of the wave function psi. So second derivative over coordinate would be equal to this expression. From here we get that p squared psi is expressed through this derivative. The same we can do with the time derivative and find that E times psi is equal to the derivative in time. Now we use the results of these two equations, 16 and 17, put it in equation 15, and get the Schrödinger equation for a non-relativistic particle with no spin in a potential way. Now we can also remember the continuity equation and quantum description. For some volume vol, where no particles are created or destroyed, the charge conservation is given by the following equation. We have minus d rho over dt, which corresponds to the decrease of number of particles in this volume, is equal to the divergence of particle current, number of particles leaving this volume. Or equivalently, we can write down it like this. So in this case, rho is charge density and J is the current or the flux of rho. Now, what is the connection between the above continuity equation here in electromagnetism and the quantum mechanical description? We need to find how rho and J look like in quantum mechanical formalism. For this, we start with the Schrödinger equation for a free particle, so potential is equal to 0. We get the Schrödinger equation, multiply it by psi star, and take the complex conjugate, multiply by psi, and subtract the 2. So from this, we'll get the following expression, which we can simplify further and find out the expression which looks like this. The form of this expression is exactly as the one for continuity equation before. From here, you can get that rho is equal to psi star or psi squared, and J is equal to this expression. So we found basically the probability density and the current corresponding to this probability density. If we switch to natural units, which with h bar equal to c equal to 1 for a plane wave, we'll get the following expression. In this case, rho would be equal to n squared, and J would be equal to n squared times v, the velocity of the particles. So we see here that the number of particles per unit volume is equal to n squared, and for n squared particles per unit volume moving at velocity v, we have n squared v particle passing through a unit area per unit time, which corresponds to particle flux. Therefore, J is a vector in the particle's direction with magnitude equal to the flux. Following the same spirit, Oscar Klein and Walter Gordon made an attempt to find quantum mechanical equation which describes relativistic electron. For this, they started from the relativistic relation between energy and momentum for a free particle and replaced E and P with the corresponding operators. So finally, they got Klein-Gordon equation for a relativistic particle at no spin, which looks like this. Using the following notations for d mu and d mu product, we can write down Klein-Gordon equation in the following way. This equation has some problems. For example, for the plane wave solution psi, which we had previously, the Klein-Gordon equation gives the following expression, and here we find that energy can be equal to plus minus square root of p squared plus m squared, which is the same result which in principle one can get directly from the equation 27 here. Historically, these negative solutions were viewed as problematic because they imply that there is no ground state in the atoms and the transition to the lower energy states were always possible. Also, what we can do is proceed as before and to calculate the probability and current densities according to the expressions which we derived previously. For the plane wave, we will get that probability is equal to 2e n squared and J is equal to n squared p. So particle densities again are proportional to the energy. Remember our convention of the wave function normalization discussed in the previous lecture, so this is connected. And you can see that the rho can be also negative. The question is, how the probability can be negative? No interpretation could be made at that time. So basically in 1928, there were two main problems with the Klein-Gordon equation. First is negative energy solutions, and second, negative particle densities associated with the solutions. And in fact, now in quantum field theory, these problems are overcome, and the Klein-Gordon equation is used to describe spin-zero particles, like for example, pions. But back in the day, these problems led to new developments. They motivated Dirac to search for a different formulation of relativistic quantum mechanics in which all particle densities would be positive. The resulting wave equation had solutions which not only solved this problem, but also fully described the intrinsic spin and magnetic moment of the electron. So let's look back at the Schrödinger equation. As you can see, it has first order of derivative in time and second order of derivative in the coordinate. The Klein-Gordon equation has a second order of derivative throughout. Now Dirac looked for an alternative which has the first order derivative throughout. So he was looking for the expression in terms of alpha times p plus beta plus m psi is equal to the derivative of psi over time. So in this case, basically p is derivative, first order derivative in coordinate, and alpha and beta some unknown coefficients which Dirac wanted to find. Now what we need to do is to have a bit of math and write down the previous equation in full and then square it. So here we just expanded our momentum operator and then took the square of this equation. At the end, in this equation, we have several components: second derivative over coordinates, mixed derivative over coordinates, and first order derivative over coordinates. And all this should be always equal to the second derivative over time. Now, for this to be a reasonable formulation of relativistic quantum mechanics, a free particle must also obey the E squared equal to P squared plus M squared relation. So it must satisfy the Klein-Gordon equation as well. Therefore, basically this huge expression here, which consists of three lines, should be equivalent to the Klein-Gordon equation. For this equivalency to always be true, the coefficients alpha and beta should behave in the following way. Alpha x squared, alpha y, and alpha z squared should be equal to beta squared equal to 1. And alpha and beta should anti-commute, as well as alphas of different directions also should anti-commute. Obviously, from here, alpha and beta cannot be numbers, and this equation requires 4 mutually anti-commuting matrices, and they must be at least 4 times 4 matrices. Consequently, the wave function must be a 4-component Dirac spinor. It has new degrees of freedom as a result of introducing an equation that is first order in time-space derivative. So psi is here some vector of 4 objects. Now, for the Hamiltonian to be Hermitian, we need that this alpha and beta matrices also should be Hermitian, and they should be anti-commuting according to our previous expression. In principle, there can be several explicit representations for these matrices, but we can choose one of them which is convenient for us. Of course, we should know that physical results don't depend on the actual particular representation. So everything what is needed is described in these commutation relations. A convenient choice is based on the Pauli spin matrices. So beta would be equal to 4x4 matrix formed by a unity matrix and minus unity matrix here. And alpha matrices are formed by the Pauli spin matrices, sigma, which look like this. All these matrices are Hermitian and anti-commute with each other. Now let's get back to the probability density and current, which were in trouble with the Klein-Gordon equation. The Dirac equation looks like this. its Hermitian conjugate looks like this. What we can do again is to compute psi dagger times equation 53 minus equation 54 times psi, taking into account that alpha and beta are Hermitian and taking into account that such expression can be written down as derivative of psi dagger alpha x psi over the dx. From here, we get a continuity equation like this. So basically, from here, we obtain that the probability density rho is equal to psi dagger psi, and current is equal to psi dagger alpha psi. So rho in this case is the square of the wave function and is always positive. So basically, here we do not have this ambiguity which we got with the Klein-Gordon equation. And the solutions to the Dirac equation are the four-component Dirac spinors. So basically, great success of the Dirac equation is that these components naturally give rise to the property of the intrinsic spin of a particle. The Dirac equation can be written more elegantly by introducing the four Dirac gamma matrices. So gamma 0 is defined equal to be beta matrix, gamma 1 is beta times alpha x, gamma 2 beta times alpha y, gamma 3 is beta times alpha z. If you multiply equation 53, this one, by minus beta, we'll get the following equation. Then we replace here products of beta and alpha with gamma matrices. And using again the notation of the d mu, we can rewrite it in the following way. Now, you should remember that Dirac gamma matrices are not four vectors. They are just constant matrices which remain invariant under a Lorentz transformation. Now, let's look at some solutions of the Dirac equation. We can consider a particle at rest, with momentum equal to 0, and therefore the Dirac equation would simplify to this part. So p is equal to 0, you get only derivative over time and n, and see that spinor psi naturally would split into two component B spinors, psi a and psi 2. It's evident from this equation. So from here we have separate equation to psi a and psi b. And the solutions can be written as a function of the bispinors UA and UB. Psi A is equal to UA times E minus EMT for positive energy solution and UB for the negative energy solution. Now we can go back to the equation 63 and write down it in the following way. Since left-hand side here is diagonal, we can find decoupled solutions for UA and UB and choose them as a set of eigenvectors. Like for example, you can take UA equal to 1, 0, or UA equal to 0, 1 for the positive energy, and UB equal to 1, 0, or 0, 1 for negative energy. Putting all together for a particle at rest, we find the following solutions. Top ones for the positive energy and bottom ones for the negative one. Now, the fact that there are two identical fermions with the same energy implies that there is another quantum number that allows to distinguish them, the helicity. The corresponding operator is the operator projecting the spin in the direction of motion. So here you can see direction of motion of the particle, P, and then spin can be either directed in the same direction as motion, so we have helicity H equal to +1, positive helicity, or spin can be opposite to the direction of motion, and we will have negative helicity particle here. Now, in Dirac equation, we still had negative energy solutions, and Dirac was trying to explain them as well. So we know that atoms are observed to be stable, and when an electron is on a high energy level, it undergoes transition down to the state of lowest positive energy, which is not yet occupied by two electrons. So to save his equation, Dirac made the hypothesis that all the states of negative energy are already occupied by two electrons, preventing another electron to reach the states. And all these electrons filling the negative states form what was called the Dirac sea. Now, if some sufficient energy is provided to an electron of the sea, so it jumps up, then the absence of the electron here appears as the hole in the sea. And then missing charge of minus E value looks the same as the presence of the positive charge. Therefore, missing particle with negative energy is presence of a particle with positive energy. Basically, the explanation was that a hole in the electron sea at negative energy level looks like an ordinary particle with charge equal to plus E and energy minus E, which is greater than 0. And then the question is, would such positive electron exist? So if so, then such a positive electron should be identical to the electrons except for their charge. The mystery of negative energy solutions of Dirac's equations was there until 1932, when Anderson discovered the new particles which seemed identical to electron but with an opposite charge. So you can see an event display here. He used a cloud chamber, a tube full of supersaturated liquid, and charged particles passing through this liquid were ionizing it, so leaving the visible track, which could have been photographed. Then uniform magnetic field was applied, B here, and there was a 6 millimeter lead plate positioned there. So basically what he saw was a track of positively charged particle for which the energy loss in this lead plate was not compatible with energy loss expected from a proton. But in principle, this track looked exactly like an electron except for a charge. So this basically constituted the very first observation of an antiparticle, an anti-electron, which was called positron. Finally, in 1933, Dirac, together with Schrödinger, received Nobel Prize, and in 1936, Anderson, at the age of 31, became the second youngest Nobel Prize winner ever. Later, in 1940, Feynman-Stuckelberg interpretation appeared for the negative energies, which basically we are using until now. So the story of the sea of the electrons was not very satisfactory, since it would imply having infinite negative charge of the universe. A new hypothesis was supported by the positron observation. Basically, to each particle of mass m and charge q, there should be an antiparticle of mass m and charge minus q. And the solution with negative energy can be seen instead as the positive energy particle moving backwards in time. So you can see here, if you have electron moving backwards in time, is the same as positron moving forward in time. Nowadays, there is an antiparticle associated to each known particle, making the positron discovery one of the milestones of contemporary particle physics.